So they're playing like the Dungeons and Dragons inside. Oh my god. We have like a league of that back home. I drive past the park and they're just outside with like a sword and a makeshift.
Yeah, that's called LARPs. LARPs.
But they call it Watts for some reason. I don't know why.
LARPS. When I did undergrad, there was a LARPing group. You'd see people wearing capes around campus and.
They bring it to school.
Huh?
I've seen that here.
Yeah. But then you'd also see those same people like out in the quad with like garbage can lids as shields, and they had like swords. They actually like crafted.
Like a big foam sword.
No.
Metal one.
No, we're talking that they like used blacksmithing skills.
Oh.
You'd see them outside with like normal hammers and like like trash cans filled with fire and forging their weapons.
And they couldn't bother to do that with
These
the
are
shield.
teenagers with like nerf material and tape.
Yeah, no, not back in that day. There were people carrying around like sharpened broadswords on campus.
So they forged the swords, but they didn't forge the shields. Or did some of them do that?
Yeah, maybe some of them did. All I remember is garbage can lids.
The rules say they have to level up their smithing skills.
I mean, that was.
RuneScape. Oh,
I could just see somebody like he damages one of his swords or something like that. And says, "I must go meet the smith." Who? Jake. Jake's the smith. State Farm. That's right. Okay. So let's. Any of you who weren't here the night before, right before break, I handed back the exam. So just come up after class and I'll give you your exam back. Just a quick review to what we did right before the exam. We were talking about tables, and then we want to take that skill set and apply it to something new today. If you remember correctly, let me go to our tables. We created a table in here for mapping. Remember we were doing our number conversion dealy flippy, where we were converting numbers from base 10 to base 16 or base 8 or whatever it is. Okay. So we created a little table in here. So think of a table kind of like a spreadsheet. It's GameSalad's way of simulating a database, something being able to store things. So what we did is we filled up a single row in this table, a single column rather. So column 1 is filled up with all of the hexadecimal digits. That is 0 through 9, then A through F. And you'll notice that a 0 is at bucket 1, a 2 is at bucket, or a 1 is at bucket 2, so on and so forth. So an F is at bucket 16. Now, I call these buckets, but row 16. So I'm trying to map these to a tool that we use in programming languages called arrays. But really, tables are even a little more than arrays, but arrays are a decent start. Do we talk about arrays in here? Did we talk about memory and stuff like that?
A little bit.
I'm not getting anything from you guys on this matter. This looks like no.
Yeah, I don't think anybody's really
just
bad.
the whole.
Okay, so we just talked about this,
Right.
just at this level.
With the weather being nice, everybody's still
Memory, all we've said is basically how do humans solve problems. I think is the only way we've touched on that.
Okay. All right. So I'm going to come back to arrays here in a few minutes, and we're going to talk about them a little more depth. But let's go back and finish reviewing tables. All right. So we created this table. Now, in hexadecimal, an F is associated with the number 15. So if we had a remainder of 15, that actually becomes the remainder F. Remainder 14 is actually remainder E, so on and so forth. So based on the way that we're kind of forced to set up our table here, where rows are 1 based instead of 0 indexed. So our very first row isn't row 0, it's row 1. So based on that, we're going to have to subtract 1 from each of our rows in order to get our corresponding remainder. So if we had a remainder of 15, we'd have an F. So on and so forth. 14 would be an E, 13 would be a D, so on and so forth. Okay? A remainder of 6 would be a 6. So notice I'm actually subtracting 1 from the row. So we're going to have to do that math on our own inside the code. Okay? So this was the table that we set up that allowed us to do that mapping. Then what we did is in our code, we had a timer, and this thing happened every 1 second. That's when we actually went and kept doing the division until it finally had a remainder of 0. Okay, so as long as our game's decimal was greater than 0, because we kept dividing it and keeping the remainder, so on and so forth, what did we do? We set the current remainder to whatever our current game's decimal is, mod the base. So if we were converting this to base 16, we take whatever the current decimal is, divide it by 16, record the remainder, store that remainder inside of a variable called current remainder. Okay? So at all times, our current remainder global variable was set equal to the current remainder of our last division. Then we actually did the division. Well, actually, we did the answer. So we took, here's where we do our division. We do our division third. We could have done it second. It didn't matter. So we set the game's decimal. After we got our remainder, we changed the game's decimal to be whatever it currently was, divided by to base. So if we were doing this by base 16, we take the decimal divided by 16, we store the floor of that value. That truncates, takes the decimal point off. Okay? So that order was important. We got the remainder first, then we changed the decimal to be whatever it was divided by, in our latest example, 16. Okay? In the middle here, we updated our answer. Remember, our answer was a string we kept concatenating onto. Okay? So we set our answer to be, now remember, when we do our conversion, we do all the modulus, and then we read our answer from bottom up. Okay? That's why we're actually concatenating on our mapped value before the current version of answer. Let me just open this. That'll be the easiest way to see it. Okay? So, my current answer is self.answer. Self.the_answer. That's, if we're dealing with the answer is BAD, maybe it's currently AD. Okay? And then the last thing we're going to get is the B. And we're putting that onto the front of it. Okay? Now, this is something we introduced when we were talking about tables. We have this thing called a table cell value. The first input, first parameter of table cell value is the name of the table we're extracting a value out of. So we're extracting a value from our map table. All right? Then we want to get our current remainder and we want to add 1 to it. Okay? So if our current remainder is 6, we want to add 1 to it to give us 7. And what are we going to do? We want to get the corresponding value from column 1. So we're always going to be getting our value from column 1. And if the remainder was 5, because we do 0-based remainders, right? We added 1 to that. A remainder of 0 actually is associated with row 1. That's why we're adding 1. A remainder of 1 is actually associated with row 2. Does that make sense? So that's why we're adding 1 to this value. So we're saying go to this table, get this row from this column. Okay, that allowed us to do that mapping so that 10s became A's and 11s became B's and those kind of things. Okay? So that's how tables worked. So that saved us a lot of time rather than having to have that gigantic if statement that said if it's a 10, do this. If it's an 11, do this. If it's a 12, do this. If it's a 0 through 9, do this. That makes sense? Okay, so that's how tables worked. Now, right now, I think at our game's attribute level, we are converting 2989, the decimal number 2989, into base 16. And that should be BAD. I just happen to like that hexadecimal number, so I use it for almost all my examples. So this is what we're going to start with. So every 1 second, we should see the answer build up. Okay? And it's using that mapping to do it. So there's the D, there's the A, there's the B. And that's where we're concatenating onto the front. That make sense? Okay. So that's how tables work in GameSalad. It allows us to take a lot of that logic we were doing with a bunch of if statements and put it inside of a table. All right, questions about tables in general? Okay, now let's go and let's talk about the concept of arrays from a generalistic programming perspective. So an array is a collection of like elements under a single variable name. That's the value that we have with arrays. Now, tables sort of give us an array equivalent. As we're using our current table, we're using it like it's an array. That is, we have a single variable name, map underscore TB, or map table. Then we're using indexes, so 1 through 16, and the corresponding values from the single column. So we're treating our table like an array currently. That isn't to say that we couldn't take our table and have more values in the additional columns. Then it becomes a 2-dimensional array, or 3-dimensional array, or a 4-dimensional array, and then it stops making sense for how arrays are usually used. But since we're currently using it like an array, let's talk about arrays. So we have a current single variable name. So let's kind of mimic this for arrays. So we have a single variable name that we've currently called map underscore TB. That's our array, okay? And map underscore TB points to this place up in memory. I'm going to do a very small subset of our 16 value array. Let's just do 4 of these. Okay, so our first 4 would be 0, have a value of 0, a value of 1, a value of 2, and a value of 3. All right, that's what our first 4 values in our, if we kept going, we'd have an A, a B, a C, a D, an E, and an F. Right, this is going to get unwieldy fast if I try to do the whole thing. Now, in our current world, the 0 is at bucket 1. The 1 is at bucket 2. The 2 is at bucket 3. The 3 is at bucket 4, or index 4. Okay, I usually refer to them as buckets, so get used to my lingo. So arrays in Game Salad, tables in Game Salad are 1-based indexed. So the very first element of an array, the very first element of a table is at row 1. Now that differs from Java, and actually most modern high-level languages. Most modern high-level languages are 0-based indexes. So this would be bucket 0, bucket 1, bucket 2, bucket 3, which actually matches up to our mapping a little bit better. A 0 is at 0, a 1 is at 1, a 2 is at 2, a 3 is at 3, a F is at 15. Okay? So that would be one difference between Java and Game Salad, is that Game Salad is 1-based for indices, where Java is 0-based for indices. Not the end of the world, we just might have to do a little add 1, subtract 1, that kind of crap. Okay? So here's my values, and here's the indexes. I'll even label those out here. These are the vals. And these are the indices? Indexes. That looks good enough, doesn't it?
Yeah, either way we know what you're talking about.
Yeah. Which is the correct thing, though?
I think it's indices.
Or are they both legit? Huh? It's indices? Indexes isn't a real word? Yeah, I kind of feel like it is, too.
It's indices.
But I tend to agree that the correct use is indices, but is indexes a real word?
Yeah.
Oh, I got you. So there are different Why don't they just use indices for that? Well, I think he's right. Yeah, I think things that are indexes, like stock indexes, we could say. Then you have the NASDAQ, you have the S&P, so those are various indexes.
Can be either.
Can be either. So I'm right. Ha! First time for everything, right? Okay. I don't know if you guys saw, and I don't know why this just came up in my head, but last Thursday we did a Butterburger pilgrimage up to Green Bay. Me and a couple of friends and a couple of students came who were here over break. And so there's two competing places in Green Bay called Kroll's. There's Kroll's East, and then there's Kroll's West. Kroll's West is right across from Lambeau Field. They both claim to be the original Butterburger in Green Bay. Both claim since 1936, blah, blah, blah. So we went to Kroll's East for lunch, then we went to Kroll's West for lunch, and had Butterburgers at both. But when I was at Kroll's East, they sold their chili by the gallon. And I said I have a policy. If you're at a place that sells chili by the gallon, you have to buy a gallon of chili. That only makes sense, right? So we went there for Butterburgers, and my bill was like $100. I bought a gallon of chili and bought food for a bunch of other people, and it was a good time. So yeah, that's what I did over break. We did a Butterburger pilgrimage. Okay, so these are the values stored in our array. These are the actual indexes in our array. Now, mapTB would be the name of our variable. So I'm kind of connecting this to Java, how the two work together. Now, the reality here is, these are integers, right? Let's just treat them as integers for right now, even though we know the later values are actually chars. Well, we can treat them as chars. We can treat them all as chars, that's fine. So the values here, actually, this is the character 0, the character 1, the character 2, and the character 3. That's what's actually stored there. Later on, there'll be the character A, the character B, the character C. All right. Now, something we don't often think about when we deal with variables is that variables are actually stored somewhere in memory. See, modern day computer scientists, we typically don't really think about memory because memory's scary. Okay, we don't think about hardware anymore. Everything has become more and more user-friendly to the point that we don't even have to think about it. How many of you have built your own computer? I think if you're in the one, how many of you, several of you are probably in the 175 class right now, right?
Yeah.
Have you guys actually built it yet, or you guys just talked about building it?
We talked about that.
Okay, because you're going to be building a computer at some
Waiting on
point.
the parts.
Okay.
I think most of them are done.
So historically, when you were going to go to do that, building a computer was a fairly, I don't know, like difficult thing. I mean, not horrifically difficult. I'm sure way back in the day when you bought computer kits where you had to solder stuff together and things like that, that was more difficult. But when I was building computers in the early 90s, let's say, you would get your processor, and processors, if you look at your motherboard, so the different pieces you're going to be working with in 175, you'll have a motherboard, you'll have your RAM, you'll have your processor, you'll have a graphics card, that kind of stuff. Well, you'd have your motherboard, which is just a giant green thing that's the heart of everything, and it would have a spot for the processor. But the processor, has pins on the bottom of it. But in the early days, well, today if you do that, what you're going to do is it has a zero insertion force socket for the processor. So you'll lift up this little arm, you'll gently lay the processor on top of it, and it'll just drop it. And you put the arm down, done, processor installed. Well, before you had zero insertion force, you had to position the processor so that all the pins were immediately above the right place, and then pound it into place without bending any of the pins. Okay, this was difficult because those processors have like 600 pins on the bottom of them, especially now. Back then they probably had, I don't know, let's say 150 pins, something like that. But a lot of pins that at least one could get bent pretty easily. Same thing with memory, but even installing that processor. Now, when you put the processor in the motherboard, you just put it in there, close the thing, put your heatsink on, turn the computer on, and it automatically detects what kind of processor it is. Okay? It knows the clock speed, because what there's something called a frontside bus. These are all things you'll probably talk about in 175. But the frontside bus is a clock speed. It has a megahertz or a gigahertz associated with it. And then there's a clock multiplier, another number. And the multiplier times the speed of the frontside bus, when you put those things together, that should equal the gigahertz rating of your processor. It should be that speed. Well, you used to have to set that manually. Now, once things got better, you could do it with dip switches, where you get in there with like a toothpick or something like that. But before that, you had jumpers. These little plastic things that were so good at getting lost. And you'd use tweezers. And you'd pull the jumper off, and then you had to look at this chart like, okay, well, if I'm going to have a frontside bus speed of 133 megahertz, which that used to be fast, then we need to have our jumper configuration like this. And I mean, it was like serious work to do that. Well, so in any case, we've moved farther and farther and farther away from thinking about the internals of our hardware, right? So modern day computer programmers tend to shy away from memory. Yet memory's still there. Memory is still very much used. And we have this concept of something called a pointer, which terrifies programmers for some reason. Now, remember we talked about primitive types? What's a primitive type? We talked about some examples of the primitive types in Java. We had int, char, byte, boolean, short, long, okay, double, float. And we have some equivalents to our variable types in GameSolid through our attributes. We have like text and real number and integer, those types of things. Well, primitive types are variable types that can only hold a value. So that would be pretty similar to what we have with our attributes in GameSolid. They're built for holding a single value, right? Whereas our actors in GameSolid would be more like object type variables in Java, where they can hold values because our actors can have a whole bunch of attributes associated with them, correct? But they can also do more. They have behaviors and crap like that associated with them. So if we're making that comparison, we're going to say in Java, we have primitive types and we have object type variables. In GameSolid, our primitive types are attributes. Our object types are actors. Okay? Now, one of the primitive types in a historical language like C or C++ is something called a pointer. All a pointer is, just like any other primitive type, it's just built for holding a value, is a variable for holding a memory address. And interestingly enough, memory addresses are almost always represented as hexadecimal numbers. Some point in the future, they'll probably not be represented using hexadecimal numbers. Why do you think memory is represented using hexadecimal numbers rather than decimal numbers? Memory in and of itself is a giant array. Okay, so when you put those sticks of memory into your computer, they're all linked together, and they create a giant array, something that looks similar to this. And each bucket of that array holds a value. Okay, that's where our stuff in our computer is stored. Random access stuff, things that need to be really, really fast that are stored during the runtime of a program. As opposed to our programs themselves, they're stored on our hard drive in between boots of our computer. So when we double click on it, it's copied from our hard drive, which is relatively speaking slow, into RAM, which is relatively speaking fast. Okay? So our memory in our computer is fast storage for pieces of information, and it's set up like an array. So a bunch of buckets to hold different pieces of information. A pointer is a value that allows us to know where in memory a certain other value is stored. Okay, we'll talk about it through example here in a second. Okay, but back to the question I asked, since it's kind of related to the hexadecimal numbers that we've been talking about, conversion and things like that. Why do you think memory addresses are represented as hexadecimal values? What's the advantage of hexadecimal over decimal? Like, why do we even have hexadecimal? I mean, decimal is infinite, right? Can't you just keep counting? There's always going to be one bigger number, right?
Yeah, it should be.
Okay. So it's not like we're running out of numbers with decimal. Go ahead.
There are more combinations. One of the big numbers, you Combine them in more ways.
Combine them in more ways.
Round up.
I don't know.
Well,
Hold more values in a smaller set.
that's it. You can hold more values in a smaller space.
Yeah.
So if we're looking at something here, if we're going to our game's attributes, these are equivalent values. 2989 and BAD are the same, well, you saw it there. BAD are the same value. Does that make sense? One of them is the hexadecimal representation, the other one is the decimal representation. Now, this one's only 1 digit smaller, but you can extrapolate and see how that would scale, where very, very, very large decimal numbers can be represented in a much smaller footprint with hexadecimal numbers. Well, why is that necessary if decimal numbers are infinite? It's not like we represent a larger value in hexadecimal than we can represent in decimal. No, come up with the biggest number that you could come up with. Just quintillion something, or whatever, just some gigantic number, and then you can go and Google it and find out that's like not even halfway there to what we have names for. And then we have the stuff we don't even have names for, right? So come up with the biggest number you can think of. Can you represent that number in both hexadecimal and decimal? Absolutely. So why does hexadecimal exist? Did somebody just decide we want to be difficult? Well, he mentioned that smaller footprint. Go ahead.
We don't have unlimited memory.
That's it. So our computers, while we can represent any number mathematically, our computers don't have unlimited memory. So if we can represent bigger numbers in smaller footprints, we can fit them in smaller containers. Okay? So by having hexadecimal values, if we decide that our memory map let's say that we have let's just be a little bit historical here, that way the numbers don't get too out of whack. Let's say we have a 32-bit memory manager. So the memory manager for Windows and the memory manager for your Mac, let's just say it's 32-bit. Most of them today are 64-bit, modernly. But that wasn't until very recently. Even just a couple years ago, a lot of them were still 32-bit. That means that each bucket of memory was represented by a 32-bit number for its indice. All right, well, what's the biggest 32-bit number we can come up with? "32 bits is 32 zeros and ones, correct? Now, a indice doesn't have to be able to store negative numbers, right? So we can go 0 to something. So really, our indices would be 32-bit unsigned I'm just going to keep doing it. Integers. Okay, 32-bit unsigned integers. So this would be in the range of 0 to 8 billion. Okay? 0 to 8 billion are our values. Now, those are the number of buckets of memory that we can address. We cannot get to bucket 9 billion because we can't store that inside of a 32-bit integer. Does that make sense? So there's going to be a limit to how big memory can be, or how big memory can be addressed, because we're going to run out of numbers to keep indexing it. So then we need to go to a 64-bit memory manager in order to index larger memory subsets. Okay, so we have kind of multiple problems here that are all fighting each other. One problem is we don't have unlimited memory, but another problem is even if we did have unlimited memory, we don't have unlimited storage space for our numbers to index all the buckets of memory. Kind of make sense? So we can index more buckets of memory with a 16-bit value if we're storing that 16-bit value as a hexadecimal number and doing the translation during runtime to get to the right index. So instead of going to bucket 2989, we're going to go to bucket BAD. Does that make sense? BAD had a smaller footprint, so it's as far as the numbers we can represent in that footprint, okay, and with that number size, BAD would be earlier in the subset, earlier in the index than 2989 would be in terms of our capabilities. All right, so that's kind of the high-level version of how memory kind of works. So every bucket of our memory is represented by something. Now I drew this extra line up here. Let's just say that map held memory address 100, which is technically a legal hexadecimal number, right? Hexadecimal is 0 through 9, A through F, so that fits the bill of, that's made up of a bunch of digits that are at least somewhere in that set. Okay, so this is memory address 100 in hex. That would probably be represented like this, 100 hex. That's the memory address. Now, but let's keep it in decimal just for this example, for the math. In Java, integers are 32 bits. In Java, chars are 16 bits. They represent the Unicode character set. Okay, so a char is a 16-bit unsigned number. That's what a char is. And 16 bits is also can be thought of as 2 bytes. A byte is 8 bits. Okay? So if map holds 100, that means this is memory address 100. This is memory address 102. (104), 106, okay? So bucket 1 or bucket 0, if this was in Java, we'd say this is 0, this is 1, this is 2, this is 3. So bucket 0 holds the value, 0 in this case, and it's at memory address 100. Bucket 1 holds the value 1 and is at memory address 102. Bucket 2 holds the value 2 and is at memory address 104. So on and so forth. MapTB is a pointer. This guy is said to point to the base address of this array. So this array lives in memory in contiguous memory, memory in a row. Okay? So this variable holds a memory address which points into memory to the beginning of the array. In Java, the syntax, actually, map underscore TB at bucket 0. This guy right here would boil down to the char 0. This would be the value that lives at index 0 of MapTB. And the way it got that value, this is the same thing as saying MapTB plus 0 times size of char. Which is the same thing as saying 100 plus 0 times 2, which is 100. Bucket 0 of MapTB is located at memory address 100, and its value is 0. Similarly, if I say, give me index 1, that would be MapTB plus 1 times size of char, or 100 plus 1 times 2, or 102. Bucket 1 lives at memory address 102 and has a value of 1. Does that make sense? So arrays can be mathematically calculated. The position of those arrays can be mathematically calculated. So, and remember, tables in GameSolid are just sort of like arrays. So I'm kind of using this opportunity to explain how array structures work in most high-level programming languages. This isn't necessarily how it works in GameSolid, but we can pretend like it is. Go ahead.
How did you define the size of chars too?
That's the Java. Chars are 16-bit unsigned integers.
Okay,
So it's 2 bytes. 16 bits is 2 bytes. All right, so where I use this, and we'll review this next semester when you do the 250 class, where we really talk about this from a Java point of view, but just to kind of give you a precursor, most Java textbooks claim that pointers don't exist in Java. The reality is almost everything in Java is a pointer. So what doesn't exist in Java is a special syntax for pointers. See, in Java, we would say, give me the value at bucket 0 with a syntax that looks like this. In an older language, like C, the equivalent to that, I mean, you could use that syntax in C, that'll work. But you could also use pointer syntax that says map TB plus 1 times size of char star. This right here is identical to this right here. It means the same thing. This is pointer math. This is saying, so everything before the asterisk here is just a math problem. It says take this address and add to it 1 times the size of a char to give me a brand new memory address. The asterisk says give me the value at that memory address. So older languages like C and C++ had a special syntax through the asterisk for dealing with pointers. Asterisk means give me the value at that memory address. Ampersand says give me the address. Okay? Java did away with a special syntax for pointers and just treats everything like a pointer. Therefore, textbooks are tricked into saying pointers don't exist. Okay, and we'll cover that ad nauseum next semester, but just kind of where things are going here. All right. So, in any case, arrays are collections of values. So this is what we want to get out of this lesson. Okay? This is all the under the hood stuff. It would be great if you completely understood this stuff. At the very least, I want you to appreciate that it's there. Next semester, I'll probably ask you questions to really deal with it. In this class, I probably won't ask you to do any pointer math stuff because it's not directly related to GameSolid. It's more of a teaching opportunity for what's coming. Okay? But I want us to understand that arrays are collections of values, and having collections of values is a benefit in any programming language. Okay? Being able to store stuff in an indexed way is beneficial to us. All right? So we have collections of values with associated indices. This is the important part. The fact that they have to live somewhere in memory is important because that's how it works, but isn't important to use it. Okay? You don't need to understand, well, technically our table lives at memory address this, and that means something to us. That's all the work that the operating system is doing for us. The operating system is saying, oh, you want to store that? No problem. I will go and do all the heavy lifting and figure out the right way to store that in real memory for you. All you have to do is say, I want the table at index 4, column 1. Okay? And it does the magic for you behind the scenes. But just understand kind of what's underneath the hood of our car here, at least a little bit. Appreciate what's there. All right. Now, that's kind of the story of arrays, if you will. So now we're back to tables. Tables are like arrays if the table has only one column. They're like two-dimensional arrays if it has two columns. They're like three-dimensional arrays that have three columns. After that, it's something new. You would very, 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 very rarely in any high-level language see anybody use more than a three-dimensional array. Think of a three-dimensional array like a cube. Okay? So a table, because we're calling it a table, we wouldn't think of it like a cube. We could, but we would just think of it as, here's our indexes. Here's column 1 has certain values, column 2 has some values, column 3 has some values. Make sense? So tables are like arrays if they only have one column. I would say it's fair to say they are like parallel arrays if there is more than one column. Now, what's a parallel array? Parallel arrays are when you have two arrays where bucket 0 of this array is related in some way to bucket 0 of this array. Bucket 1 of this array is related in some way of bucket 1 in this array, so on and so forth. Okay, we call those parallel arrays. In the future, we solve those through objects. It's like you need something that store more than one value under a single name, no problem. We'll create a car object and it can store number of passengers and weight. No big deal. Okay, we could already do that with GameSalad through actors. But a table can be used like an array if it only has one column. It can be used like a parallel array if it has more than one column. Similarly, it can be used like a database if there is more than one column. That is to say, there is no rule that says we must have column 1 be related to the stuff that's in column 2, be related to the stuff that's in column 3. We might just choose to keep track of, oh, I'm storing this kind of stuff in column 1, I'm storing this kind of stuff in column 2, I'm storing this kind of stuff in column 3. Does that make sense? We may not choose to relate them. If they're not related, though, then utilizing the indices to tell them apart might become more cryptic. Okay, otherwise we could say, well, bucket 0 of this guy is related to bucket 0 of this guy. Bucket 5 of this guy is related to bucket 5 of this guy. Now we can use the indices to get all of our various values. If those columns have nothing to do with each other, the indexes kind of get thrown out the window, where maybe column 1 bucket 5 means one thing. Column 2 might not even have a bucket 5. It might just be column or bucket 1, 2, and 3. And those mean something completely different, maybe even loosely related to what's in column 1, but not directly related based on index. Okay, so tables are pretty flexible. We can use them for some different things. Now, what we want to start doing over the next couple of classes is we want to somehow harness the power of tables to represent playing cards. So what if we were building a game that was like a card game? So a playing card has a value and a suit, correct? So values are 2, 3, 4, 5, 6, 7, 8, 9, 10. Then Jack, Queen, King, Ace. We'll leave jokers out. All right, so those are our values. What are our suits? We have hearts, diamonds, clubs, and spades. So there are, what's this, 13? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's 13 values and only 4 suits. How could we use a table? Let's just say that we want to create a deck of cards. Go ahead.
Wouldn't each column be a different suit?
You could certainly do it that way. But let's say I want to create a deck of cards. So there's going to be 52 total cards, right? 52 actors, if you will, where each actor is a card. Now, I want to create 52 cards, and I need to have the values that those cards are going to be stored in a table. So you could say each column is a suit. you can say that all of column 1 is our values, all of column 2 is our suits. So you can have the 13 values in column 1, 1 through 14, and then you could have 1 through 4 be our suits in column 2. Something else you could do. No big deal, right? You could have one column that represents all of our values. Okay, or two columns that represents the value and the suits, but literally you have duplicates. So you'd have 2 of hearts, 2 of clubs, 2 of diamonds, 2 of spades. So you represent all 52 cards in 2 parallel arrays. Does that make sense? So you have 52 buckets, 1 through 53, and column 1 is the values, column 2 is the suits for all of those cards. That's one way you can represent it. That would be a parallel array version of that representation. Or you can represent it where all of column 1 is your values, so 13 values, 1 through 14. All of column 2 is 1 through 4, your suits. And you somehow play off those two things to generate 52 cards. 13 times 4 would be 52, right? Okay? Or, you can say what he said, where each of your columns represents one of your 4 suits. And each of those columns would have the same 13 things in it, right? That would probably be the worst of the 3 solutions from a duplication of value perspective, because really all 4 of those columns are identical, aren't they? Column 1 is the hearts column and has the 13 values. Column 2 is the diamonds column and has the same 13 values. So why store those 13 values in 2 separate ways, 2 separate places? If we can harness them, it doesn't mean it's wrong. It just means that it's kind of wasteful in space, which is actually kind of a new way of storing things. Historically, I'll just finish up with this. Relational databases had a goal of saving storage space because memory was at a premium. Y2K bug, all that crap. Modernly, though, most of our cloud-based data stores are, they duplicate the data a zillion times so that they can always focus on performance. They say memory is basically infinite now. Okay? We'll come back on Wednesday. We'll finish writing we'll at least start implementing our playing cards because we want to be able to represent a deck of cards.